Alright guys, let's get going with vodcast 7.5. This is a video stuff for the Honors Chem 1 class. That doesn't mean that if you're in the CP Chem class that you can't watch this and learn from it and stuff, but it does mean that you won't be tested for it and it won't be on your EOC. But for you Honors guys and gals, it definitely will be. So, what are we talking about? We're talking about, let me jump back real quick, we're talking about predicting products. So what this means is we learned about 5 types of reactions in the last vodcast, in the last section, and we're going to be able to predict the products of 3 of those. Now the good news is what that means is that there are 2 of them you don't have to worry about. So synthesis and decomposition reactions, you don't have to know the products. There are some ways to be able to know what those are or to be able to make some educated guesses, but we'll talk about those when you get to Chem 2 Honors and AP Chem next year. Okay, so the easiest of the other 3 to know is combustion reactions. So what we're going to do for each of these 3 is I just want to sort of briefly remind you of what each of these reactions is. You should have this in your notes already from vodcast 7.4, so you can check there. But if you don't, make sure that you're looking, that you can copy this stuff down there if you don't have those notes. Okay, really you should go back and get those notes because you need to get synthesis and decomposition. So remember, a combustion reaction is something that has oxygen as a reactant. That is always what sort of indicates that is a combustion reaction. This is one that we've done in lab, but we've burned magnesium in the presence of oxygen to create magnesium oxide. Predicting products is fairly simple for these, assuming this one thing. And that one thing that you have to assume if you want to predict products here is that we are using hydrocarbons. Now, what is a hydrocarbon? A hydrocarbon is something that is made of hydrogen, hydro, and carbon, hydrocarbon. Okay, so the example here is methane plus oxygen. Now, if you're burning a hydrocarbon, you are always going to get the same 2 products. You're always going to get carbon dioxide, you're always going to get water. It doesn't really matter what the hydrocarbon is. Okay, so we could burn ethane, or we could burn the ubiquitous propane that we've done many times. It could be butane, okay, gasoline, which is octane, or at least it's a combination of several different types of octane. Any of those things, in the presence of oxygen, we get CO2 and water. Those are your 2 products. So if you're asked to find products, and it's a hydrocarbon plus an oxygen, always CO2 and water. You might have to balance it afterwards, but it's always those 2 things. So that's the easy stuff. The harder stuff is when we get into single and double replacements. So for single replacements, just real briefly, remember that the way that we tell that something is a single replacement is that we've got a metal by itself on one side and then a different metal by itself on the other side. Okay, and remember that what happens is that this metal is going to replace the metal on the other compound. So the magnesium takes the place of zinc and we get magnesium nitrate instead of zinc nitrate. And then, since the zinc got replaced, it gets kicked out and it's on its own. Okay? So, a couple of quick things. First off, this doesn't always have to happen. Okay? The replacement only happens if the element by itself is more reactive than the one it's replacing. So, the way that we know that is we look at this little chart called the activity series. Okay? So, what that means is like if I have potassium and I'm trying to replace sodium in chloride, okay, I look on this chart and I see that potassium is higher up than sodium. So that means potassium is more reactive or more active, and so it's going to take sodium's place. And so if I had to predict products there, I would get KCl, and then Na would be the thing by itself. Okay. Now, this is not an exhaustive list. In fact, if you notice, everything on here except the exception of hydrogen is a metal, and hydrogen's kind of on the left side of the table anyway, so we often treat it like a metal. It can also be for halogens. So you might see something like this. You might see fluorine is trying to replace chlorine. Okay, fluorine is not a metal, so it can't replace a metal, but fluorine is a halogen, so it can replace a halogen. And since fluorine is more active than chlorine, then our final product there would be NaF plus Cl2. Okay. Now, so you say, okay, well, that's great. I've got a chart, and you guys should have that chart. In fact, I know you do, for the activity series. But what if it's one of those halogens? How do you know what replaces what? Well, in that case, you just look on the periodic table. And in the periodic table, the halogens are arranged in this order. Okay, fluorine, chlorine, bromine, and iodine. and they replace each other just like the activity series. The ones that are higher up are more active, and so they're going to replace the ones lower down. So fluorine always replaces the others, just like lithium will replace any of the metals. Chlorine replaces bromine and iodine. Bromine just replaces iodine. And iodine basically doesn't replace anything but can get replaced by all the others. Okay, so let's work a couple of these real quick just to see what this looks like. So we've got sodium and calcium carbonate. So we take a quick gander back at the table, and that we look at that and say that, okay, where's sodium? Sodium is right here, and calcium is right there. So do we get a replacement there? Okay, no. Okay, that brings up a good point. If the thing that you're trying to replace is not higher on the table than the thing it wants to replace, then what we do is we write no reaction. Okay, that's also going to be true in the second case. If you look at magnesium and then look at your chart, lithium is always the highest, so we would get no reaction. Okay, so if we look back on our chart here at copper and silver, they're both pretty low on the table, but copper is a little bit higher than silver. So that means copper is going to take silver's place. Okay? So the first thing you should always do when you get one of these then is just write this thing that's going to be by itself. If copper is going to take silver's place, then I've got silver left by itself. And then we have to crisscross to be able to figure out what compound we actually get. Now, sometimes you'll get a multivalent thing like copper where you don't really know the charge. We're typically just going to assume that it has a +2 charge. That's not always the case, but it's a pretty good assumption in single replacements. And so that's going to mean that in this particular case, we're going to get Cu Cl2. Again, it doesn't have to be, and I would probably tell you what that charge was if you didn't have it. Most of the time, it will be something that you'll know. It won't be one of these multivalents. So let's work one more real quick. For some strange reason, I don't know why I put the sodium and calcium one in there. I didn't mean to have two no reactions. So let's work one other one real quick. Let's take lithium, okay, plus, let's say, magnesium sulfate. Okay? So lithium's the highest thing up on the table. Go back and look at your table. Lithium's highest, definitely higher than magnesium. So lithium's going to take its place. So the first thing we do is write magnesium by itself. Okay? And then we're going to crisscross the lithium with sulfate because lithium is kicking magnesium out. So I've got lithium that has a +1 charge. Sulfate has a -2 charge. And anytime we make ionic formulas, we always crisscross them. Okay, so we get Li2SO4. All right, so that's single replacements. Definitely more difficult than the others, but not as hard as what we're going to get to now. This is really the meat of the stuff. You'll definitely see some of these on the EOC. And these are double replacement reactions. Remember that the way that we know that it's a double replacement reaction is that you've got two ionic compounds. Okay, and more to the point, when you look at those two compounds, what is going to happen, we know, is that the cations are going to switch places. Remember that the cations are the metals. They're always the first thing, and they're going to switch places. So my sodium is going to replace my cadmium. My cadmium is going to replace my sodium. So that means I'm going to get cadmium sulfide, okay, right here, and I'm going to get sodium nitrate right here. Okay, so let's talk about how to find the products when we don't know them. The easiest way to do this is sort of what I like to call the inside-out method. You'll notice that it has some similarities just a little bit to the FOIL method that you learn in algebra. So here's the way it works. I know this is double replacement because I had two ionic compounds, and they're both aqueous. They don't have to. It doesn't have to say aqueous. You can usually pretty safely assume that it is if you've got two ionic compounds like this. So here's what we've got. Outside, calcium is going to join with chlorine, and hydrogen is going to join with hydroxide. Okay, and remember, these are going to be ionic compounds, so anytime we do an ionic compound, we have to crisscross stuff. So I've got calcium that has a 2+ charge, and I'm going to pair that with chlorine that has a negative charge, okay, outside. So we crisscross that, we get a 2 and a 1, and so my first compound then, my first product is calcium chloride, okay? And then we're going to crisscross the inside pair. So I've got hydrogen, and you're thinking to yourself, why didn't I put the OH first? You always put the cation first, and hydrogen is the cation, hydroxide is the anion. So those are 1-to-1, so we crisscross them, 1, 1. And so that would give us HOH. And HOH, by the way, is what? Okay, I can almost hear you calling right now. It is H2O, okay, which is water. So those are my two products, calcium chloride and water. All right, let's try one more of these before we make this a little bit more complicated. So again, we want to do outside barium to sulfate, and then inside chlorine and hydrogen. Okay, so we got to crisscross them. Barium has a 2+ charge. Sulfate. Okay, why does it go sulfate? Okay, first off, it was with chlorine, so it's going to have to go sulfate. But remember, outside, so barium to sulfate. We crisscross those, and remember, you should always sort of put a polyatomic around your, a parentheses around your polyatomic. So I do that. Since they're both 2, remember that what we do in that case is that we reduce them. And so that's going to mean that my first product is BaSO4. 2's cancel out. I can divide both sides by 2. Okay, for my second thing, I've got hydrogen going with chlorine. Okay, hydrogen has a +1 charge, chlorine has a -1. So 1 and 1, and so my other product is HCl. Now, what happens a lot is the students get really upset and they think, well, what did you do with the subscripts here? There was an H2 here and a Cl2 here. The subscripts don't really matter as far as doing the crisscross unless they're part of a polyatomic. Like I can't lose that 4 there because that's part of what makes sulfate. But the 2's, hydrogen ions aren't in pairs, and neither are chloride ions. They're diatomic if they're by themselves, but not if they're ions. So if they're ions, it's just H+ and Cl-. Crisscross them, get your product. Now you have some balancing to do at the end, so if we were actually working this problem out and it said balance it, I'd have to put a 2 here, and that would take care of the H2 and the Cl2. Okay? Alright, so here's the thing. To actually have that happen, what we showed on the last slide, you have to have one of 3 things. You have to have a gas produced. Okay? Nothing that we did in this phase probably did a gas. HCl can be a gas, but it's probably not in this case. You have to have a liquid produced, okay? And 9 times out of 10 when you work one of these, if you get a liquid, it's going to be water. Or you have to have a solid produced. Now, in your head, you're probably thinking, doesn't that cover everything? It covers everything except kind of the big mama jama of chemistry, which is aqueous, okay? Aqueous means dissolved in water, right? That's where we get the little AQ thing that we see so often. And if everything is aqueous, it doesn't actually form a reaction. We'll get to that in a second when we do netionics. But we have to have one of these 3 things, gas, liquid, or solid. So how do I know that I have that? Like, I found my products in the last case, but I didn't give anything phases. I mean, I know that's water and that's a liquid, but I don't know if that's solid, liquid, aqueous, whatever. Okay, so how do you know? The way that you know is you look at the solubility rules. Okay, you guys have these on a chart, and so you would go back and check the things that you just found and then decide whether or not they were soluble. So we had some nitrate stuff in a previous problem, one of the single replacements. They're always soluble. It's real important to get this part up here that's up at the top. Okay, soluble means aqueous. Insoluble, meaning that it won't dissolve in water, means solid. Okay, so we got to jump back to that if necessary. So here's the way it works. Nitrate salts are always soluble. Most alkali salts are soluble. When you see the word salt, don't panic. Salt just means ionic compound. Okay, so sodium, potassium, anything with that in it, usually soluble. Most of the stuff with chlorine, bromine, and iodide are soluble. There are some exceptions. If it's normally soluble, but you get an exception, soluble means aqueous, but if it's an exception, that would mean that it's solid. So for everything that you get, you're going to jump to this table and check it out and see whether your thing is solid or aqueous. So that means you've got to let us know what the phase is. Okay? So we're going to work another problem to see how that works. This is a double replacement again. I've got lead and chlorine, and I've got potassium and nitrate, outside, inside. Okay? So lead has a 2+. How do I know that? Lead's multivalent, so how do I know it's 2+? Nitrate right here has a -1. I've got 2 of them, so lead has to be 2+. We've done a bunch of those before. So I'm going to crisscross this. So my first product is PbCl2. And we'll go back and check its phase in just a minute. Let me do the other part. So potassium and nitrate, K+, NO3, right? Crisscross those, and since they're both 1, that gives us KNO3. And so now we jump back to our table to see what we've got. Okay, so we've got lead chloride, right? So it says down here, most chloride salts are soluble except lead. Okay, so if that's an exception, then that means that it's going to be solid. Okay, what about the other one? Well, that one is sort of a double whammy. Nitrate salts are soluble, which means aqueous. Okay, good, so we already know it. But most alkali salts, and potassium is an alkali metal, so that would also make this aqueous. Okay, so it sort of adds another level of complexity there a little bit. Let's work out one more real quick just to make sure that we're okay with this. And obviously, as usual, we'll work a bunch of them in class. So hydrogen is going to go with hydroxide. Remember that OH is polyatomic. Okay, potassium is going to go with phosphate, so I'm going to crisscross those things. Hydrogen, hydroxide. Again, that gives us our HOH, which is water. Okay, so immediately I know it's okay. I know that my reaction is going to happen because water, contrary to the fact that I can't write it, water is a liquid, right? Okay, and so then let's do the middle one, potassium, okay, with a +1 charge. Phosphate, the PO4 here, has a 3 negative charge, crisscross, 3 minus 1, so that gives us our other product is K3PO4. Now, remember before we said that most alkali metals are usually soluble, so that's kind of an indicator that's probably aqueous. We'll look back real quick, and it says most phosphate salts, though, are only slightly soluble. So here's the deal. Which do you pick? Usually something being soluble trumps insolubility, typically. Okay, not always the case. And if you take Chem 2, we'll get a lot more into it, talk about equilibrium constants and all that, but in general, that's the case. So what that would mean for us in our KPO4 then is that I would probably say that that was aqueous, okay? Regardless, it doesn't really matter that much because that is liquid anyway, so that makes everything all okay. All right, so let's talk about the idea of net ionic equations. And to do net ionic equations, I want to jump back real quick and steal one of our equations from the previous slide here. So let me grab a hold of that for us. Okay, so I'm going to grab this little guy. We'll just copy him. We'll take him over here. So if you remember what our products were for this particular one, okay, and you can go back and look in your notes if necessary. Our products here were lead chloride, okay, as a solid, and potassium nitrate. And that was aqueous. Now, to do net ionic equations, like if you have a job and you get net salary, you have a gross salary. So like say you make $10 an hour and you work 10 hours, that would be $100. But then you get your check on that first day and there's not $100 there. It says that you get like $70. What happened? Well, they took out taxes and Social Security and all that stuff. So what does that leave you with? It leaves you with $70. That 70 is your net pay. Okay, so gross pay is before taxes. Net pay is your final pay. We have net ionic reactions or net ionic equations in chemistry, and what that means is that we take out all of the extra stuff, just like the taxes get taken out of your paycheck. So the real kicker here is to determine what is extra. So here's how this works. It's a step-by-step process. The first thing that you do is you take lead, okay, I'm sorry, you take everything that's aqueous, and we're going to break it up into its ions, okay? So I know that I've got lead 2+, okay, that's aqueous. And I know that I've got nitrate, okay, also aqueous. It does not matter how many. Technically, I have 2 nitrates, but I'm not going to worry about that because I'm not balancing yet. Potassium chloride is also aqueous, so I'm going to break that up into its ions. Now, why am I doing this? Okay, the reason I'm doing this is because I want to get rid of any extra ions. Any ions that aren't actually doing any work, aren't really part of the problem, we're going to get rid of. Okay, so here's the deal. You can break up anything that's aqueous, but anything that is solid does not break up. It stays together. So my lead 2 chloride is still one thing together. But my potassium nitrate definitely breaks up. So those are AQ. Sorry, I had to cram that in there. Okay, and that's a negative charge. So here's the way this works. You look at a problem like this, and what happens is you go back, and everything that is aqueous on both sides, or really is the same on both sides, but by same we mean it's in the same phase and same form, same charge, all that stuff, you cancel out. So Potassium is a +1 aqueous on the left side, on the reactant side, and a +1 aqueous on the product side. So I'm going to cancel that out. Okay. Nitrate is -1 aqueous and -1 aqueous, so I'm going to cancel that out. So those little deals right there are what we call spectator ions. Okay, spectator ions are things that don't change. Usually they're going to be aqueous on both sides, not always, but that's typically the case. And so what you do then is you write down whatever is left. So what's left in this particular case is lead 2+, right, aqueous, plus Cl minus, okay, and that leaves me with PbCl2 solid. We go back and balance. It's real easy to balance once you have the net ionic. I need 2 chlorine, so I just changed that to a 2. And this is this whole deal right here. This is our net ionic equation. It is our equation minus the spectators. We've canceled out the stuff that's the same. They're called spectators because they're kind of sitting around. They're not doing anything. It's aqueous on this side. It's aqueous on this side. It's dissolved in water, dissolved in water. Nothing has happened to it. It's the same thing on either side. What has happened is that we've gone from aqueous lead and aqueous chloride into a solid precipitate. So that's the difference. Okay? Now listen, I know that that is quite a massive amount of material. You should definitely, if you didn't get all this, go back through, look at this stuff again. You must absolutely work all the practice problems that we talk about, because I guarantee you spectators and net ionic equations are going to be on your EOC. All right? Thanks again, guys.